Chapter 9. The Legacy of Mariner. If intelligent life had existed on Venus on the afternoon of the Earth's December 14th, 1962, and if it could have seen through the clouds, it might have observed Mariner 2 approach from the night side, drift down closer, cross over to the daylight face, and move away towards the Sun to the right. The time was the equivalent of 12:34 p.m. along the Pacific coast of the United States, where the spacecraft was being tracked. Mariner 2 had reached the climax of its 180 million-mile, 109-day trip through space. The 35-minute encounter with Venus would tell Earth scientists more about our sister planet than they'd been able to learn during all the preceding centuries. Space without dust. Before Mariner, scientists theorized about the existence of clouds of cosmic dust around the Sun. A knowledge of the composition, origin, and dynamics of these minute particles is necessary for study of the origins and evolution of the solar system. Tiny particles of cosmic dust, some with masses as low as 1.3 times 10 to the power of 10 grams, or about 1/1,000,000th of a pound, were thought to be present in the solar system, and have been recorded by satellites in the near-Earth regions. These microscopic particles could be either the residue left over after our solar system was formed, some 5 billion years ago, possibly by condensation of huge masses of gas and dust clouds, or the debris deposited within our system by the far-flung and decaying tails of passing comets, or the dust trapped from galactic space by the magnetic fields of the Sun and the planets. Analysis of the more than 1,700 hours of cosmic dust detector data recovered from the flight of Mariner 2 seems to indicate that in the region between the Earth and Venus, the concentration of tiny cosmic dust particles is some 10,000 times less than that observed near the Earth. During the 129 days, including the post-encounter period, of Mariner's mission, the data showed only one dust particle impact which occurred in deep space and not near Venus. Equivalent experiments near Earth, onboard Earth satellites, have yielded over 3,700 such impacts within periods of approximately 500 hours. The cause of this heavy near-Earth concentration, the exact types of particles, and their source are still unknown. The cosmic dust experiment performed well during the Mariner mission, although some calibration difficulty was observed about 2 weeks before the Venus encounter. Possibly caused by overheating of the sensor crystal, there was no apparent effect in the electronic circuits. The ubiquitous solar wind. For some time prior to Mariner, scientists postulated the existence of a so-called plasma flow, or solar wind, streaming out from the Sun, to explain the motion of comet tails, which always point away from the Sun, perhaps repelled by the plasma, geomagnetic storms, aurora, or other such disturbances. Plasma is defined as a gas in which the atoms are dissociated into atomic nuclei and electrons, but which as a whole is electrically neutral. The solar wind was sought to drastically alter the configuration of the Sun's external magnetic field. Plasma, moving at extreme velocities, is able to carry with it lines of magnetic force originating in the Sun's corona, and to distort any fields it encounters as it moves out from the Sun. It was believed that these moving plasma currents are also capable of altering the size of a planet's field of magnetic flux. When this happens, the field on the sunlit face of the planet is compressed, and the dark side has an elongated expansion of the field. For example, the outer boundary of the Earth's magnetic field is pushed in by the solar wind to about 40,000 miles from the Earth, on the sunward side. On the dark side, the field extends out much further. The solar wind was also known to have an apparent effect on the movement of cosmic rays. As the sunspots increase in the regular 11-year cycle, the number of cosmic rays reaching the Earth from outside our solar system will decrease. Mariner 2 found that streams of plasma are constantly flowing out from the Sun. This fluctuating, extremely tenuous solar wind seems to dominate interplanetary space in our region of the solar system. The wind moves at velocities varying from about 200 to 500 miles per second, about 720,000 to 1,800,000 miles per hour. This measures up to perhaps 1,000,000 degrees in Fahrenheit within the subatomic structure. With the solar plasma spectrometer working at 10 different energy levels, Mariner required 3.7 minutes to run through a complete energy spectrum. During the 123 days when readings were made, a total of 40,000 such spectra were recorded. Plasma was monitored on 104 of those 123 days, and on every one of the spectra, the plasma was always present. Mariner showed that the energies of the particles in the solar winds are very low, on the order of a few hundred or few thousand electron volts, as compared with the billions and trillions of electron volts measured in cosmic radiation. The extreme tenuosity or low density of the solar wind is difficult to comprehend. About 10 to 20 protons, hydrogen nuclei, and electrons per cubic inch. But despite the low energy and density, solar wind particles in our region of the solar system are billions of times more numerous than cosmic rays, and, therefore, the total energy content of the winds is much greater than that of the cosmic rays. Mariner found that when the surface of the Sun was relatively inactive, the velocity of the wind was a little less than 250 miles per second, and the temperature a few 100,000 degrees. The plasma was always present, but the density and the velocity varied. Flare activity on the Sun seemed to eject clouds of plasma, greatly increasing the velocity and density of the winds. Where the particles were protons, their energies ranged from 750 to 2,500 electron volts. The experiment also showed that the velocity of the plasma apparently undergoes frequent fluctuations of this type. On approximately 20 occasions, the velocity increased within a day or two by 20 to 100%. These disturbances seem to correlate well with the magnetic storms observed on the Earth. In several cases, the sudden increase in the solar plasma flux preceded various geomagnetic effects observed on the Earth by only a short time. The Mariner solar plasma experiment was the first extensive measurement of the intensity and velocity spectrum of the solar plasma taken far enough from the Earth's field so that the Earth would have no effect on the results. High-energy particles. Fatal dosage? Speculation has long existed as to the amount of high-energy radiation from cosmic rays and particles from the Sun with energies in the millions of electron volts present within our solar system, and as to whether exposure would be fatal to a human space traveller. This high-energy type of ionizing radiation is thought to consist of the nuclei of such atoms of hydrogen, helium, and of electrons, all moving very rapidly. The individual particles are energetic enough to penetrate considerable amounts of matter. The concentration of these particles is apparently much lower than that of low-energy plasma. The experiments were designed to detect three types of high-energy radiation particles: the cosmic rays coming from outside the solar system, solar flare particles, and radiation trapped around Venus, as that which is found in the Earth's Van Allen belt. These high-energy radiation particles, also thought to affect aurorae and radio blackouts on Earth, measure from about 100,000 electron volts up to billions of volts. The distribution of this energy is thought to be uniform outside the solar system, and is assumed to move in all directions in a pattern remaining essentially constant over thousands of years. Inside the solar system, the amount of radiation reaching the Earth is apparently controlled by the magnetic fields around the interplanetary space and near the Earth. The number of cosmic rays changes by a large amount over the course of an 11-year sunspot cycle, and below a certain energy level, 5,000 MeV, few cosmic rays are present in the solar system. They are probably deflected by plasma currents or magnetic fields. Mariner's charged particles experiment indicated that cosmic radiation, bombardment by cosmic rays, both from galactic space and those particles originating in the Sun, would not have been fatal to an astronaut, at least during the 4-month period of Mariner's mission. The accumulated radiation inside the counters was only 3 roentgens, and during one solar storm recorded on October the 23rd and 24th, the dosage measured only about 1/4 Roentgen. In other words, the dosage amounts to about 1/1000th of the usually accepted half-lethal dosage, or that level at which half of the persons exposed would die. An astronaut might accept many times the dosage detected by Mariner 2 without any serious effects. The experiment also showed little variation in density of charged particles during the trip, even with a 30% decrease in distance from the Sun, and no apparent increase due to magnetically trapped particles or radiation belts near Venus as compared with interplanetary space. However, these measurements were made during a period when the Sun was slowly decreasing in activity at the end of an 11-year cycle. The sunspots will be at minimum in 1964-65, when galactic cosmic rays will sharply increase. Further experiments are needed to sample the charged particles in space under all conditions. The lack of change measured by the ionization chamber during the mission was significant. The cosmic ray flux of approximately 3 particles per square centimeter per second throughout the flight was an unusually constant value. A clear increase in high-energy particles, 10 MeV to about 800 MeV, emitted by the Sun, was noted only once. A flare-up between 7:42 and 8:45 am PST, October 23rd. The ionization chamber reading began to increase before the flare disappeared. From a background reading of 670 ion pairs per cubic centimeter per second per standard atmosphere, it went to a peak of about 18,000, varied a bit, and remained above 10,000 for 6 hours before gradually decreasing over a period of several days. Meanwhile, the flux of the particles detected by the Geiger counter rose from the background count of 3 to a peak of 16 per square centimeter per second. Ionization thus increased much more than the number of particles, indicating to the scientists that the high-energy particles coming from the Sun might have had a much lower average energy than the galactic cosmic rays. In contrast, the low-energy experiment detected on October the 23rd event, and 8 or 10 others not seen by the high-energy detectors. These must have been low-penetrating particles, excluded by the thicker walls of the high-energy instrument. These particles were perhaps protons between 0.5 and 10 MeV, or electrons between 0.04 and 0.5 MeV. At 20,000 miles from the Earth, the rate at which high-energy particles had been observed had been recorded at several thousand per second. With Mariner at approximately the same distance from Venus, the average was only 1 particle per second, as it had been during most of the month of November in space. Such a rate would indicate a low planetary magnetic field, or one that did not extend out as far as the Mariner's 21,598-mile closest approach to the surface. Mariner 2 measured and transmitted data in unprecedented quantity and quality during the long trip. In summary, Mariner showed that during the measuring period, particles were numerous in the energy ranges from a few hundred to 1,000 electron volts. Protons in the range of 0.5 to 10 MeV were not numerous, but at times the flux density was several times that of the cosmic rays. Almost no protons were shown in the 10 to 800 MeV range, except during the solar flares when the particles in this range were numerous. Above 800 MeV, primarily those cosmic rays entering interplanetary space from outside the solar system, the number decreased rapidly as the energy increased, the average total being about 3 per centimeter per second. During one 30-day period in November and December, the low-energy counter saw only 2 small increases in radiation intensity. At this time, the mean velocity of the solar wind was considerably lower than during the September and October period. This might suggest that high-velocity plasma and low-energy cosmic rays might both originate from the same solar source. A magnetic field. Prior to the Mariner 2 mission, no conclusive evidence had ever been presented concerning a Venusian magnetic field, and nothing was known about possible fluid motions in a molten core or other hypotheses concerning the interior of the planet. Scientists assumed that Venus had a field somewhat similar to the Earth's, although possibly reduced in magnitude because of the apparently slow rate of rotation and the pressure of solar plasma. Many questions had also been raised concerning the nature of the atmosphere, charged particles in the vicinity of the planet, magnetic storms, and aurora. Good magnetometer data from Mariner 2 would help solve some of these problems. Mariner's magnetometer experiment also sought verification of the existence and nature of a steady magnetic field in interplanetary space. This would be important in understanding the charged particle balance of the inner solar system. Other objectives of the experiment were to establish both the direction and the magnitude of long-period fluctuations in the interplanetary magnetic field, and to study solar disturbances and such problems in the magnohydrodynamics, which is the study of motion of charged particles and their surrounding magnetic fields, as the existence and effect of magnetized and charged plasmas in space. The strength of a planet's field is thought to be closely related to its rate of rotation. The slower the rotation, the weaker the field. As a consequence, if Venus's field is simple in structure like the Earth's, the surface field should be 5 to 10% of that of Earth. If the structure of the field is complex, the surface field in places might exceed the Earth's without increasing the field along Mariner's trajectory and observable values. Most of the phenomena associated with the Earth's magnetic field are likely to be significantly modified or completely absent in and around Venus. Auroral displays and the trappings of charged particles in radiation belts, such as our Van Allen, would be missing. The field of the Earth keeps low and moderate energy cosmic rays away from the top of the atmosphere, except in the polar regions. The cosmic ray flux at the top of Venus's atmosphere is likely to correspond everywhere to the high level found at the Earth's poles. Sun direction of scan, data readings, 18 total. In contrast to Venus, Jupiter, which is 10 times larger in mass and volume and rotates twice as fast as the Earth, has a field considerably stronger than the Earth's. The Moon has a field on the sunlit side according to the Russian measurements, which, because of the Moon's slow rotation rate, is less than 1/9% of the Earth's at the equator. Thus, a planet's rotation, if at a less rapid rate than the Earth's, seems to produce smaller magnetic fields. This theory is consequently with the idea of a planetary magnetic field resulting from the dynamo action inside the molten core of a rotating planet. The Sun, on the whole, has a fairly regular dipole field. Superimposed on this are some very large fields associated with disturbed regions, such as spots or flares, which produce fields of very great intensities. These solar fields are drawn out into space by plasma flow. Although relatively small in magnitude, these fields are an important influence on the propagation of particles, and the areas in question are very large, sometimes on the order of an astronomical unit. Mariner 2 seemed to show that in space, a generally quiet magnetic field condition was found to exist, measuring something less than 10 gamma and fluctuating over periods of 1 second to 1 minute. As Mariner made its closest approach to Venus, the magnetometer saw no significant change, a condition also noted by the radiation and solar plasma detectors. The magnetic field data looked essentially as they had in interplanetary space, without either fluctuations or smooth changes. The encounter produced no slow changes, nor was there a continuous fluctuation, as in the interplanetary regions. There was no indication of trapped particles or near-Venus modification in the flow of solar plasma. On the Earth's sunny side, a definite magnetic field exists out to 40,000 miles, and on the side away from the Sun, considerably further. If Venus's field had been similar to the Earth's, a reading of 100 to 200 gamma, a large cosmic ray count, and an absence of solar plasma should have been shown. But none of these phenomena were noted by Mariner. These results do not prove that Venus definitely has no magnetic field, but only that it was not measurable at Mariner's 21,598-mile point of closest approach. The slow rotation rate and the pressure of the solar winds probably combined to limit the field to a value 1/10 of Earth's. Since Mariner passed Venus on the sunlit side, readings are required on the dark side in order to confirm the condition of the magnetic field on that side of the planet, which normally should be considerably extended. The surface. How hot? Before Mariner, scientists had offered two main theories about the surface of Venus. It had either an electrically charged ionosphere, causing false high-temperature readings on Earth instruments, despite a cool surface, or a hot surface with clouds becoming increasingly cooler with altitude. The cool surface theory supposed an ionosphere with a layer of electrons, having a density thousands of times that of Earth's upper atmosphere. Microwave radiations from this electrical layer would cause misleading readings on Earth instruments. As a space probe scanned across such an atmosphere, it would see least amount of charged ionosphere when looking straight down, and the most concentrated amount while scanning the limb or edge. In the latter case, it would be at an angle and would show essentially a thickening effect of the atmosphere because of the curvature of the planet. As the probe approached the edge, the phenomena known as limb brightening would occur, since the instruments would see more of the electron-charged ionosphere and little, if any, of the cooler surface. The temperature readings would therefore be correspondingly higher at the limbs. The other theory, held by most scientists, visualized a hot surface on Venus, with no heavy concentration of electrons in the atmosphere, but with cooler clouds at higher altitudes. Thus, the spacecraft would look at a very hot planet from space covered by colder, thick clouds. Straight down, the microwave radiometer would see the hot surface through the clouds. When approaching the limb, the radiations would encounter a thicker concentration of atmosphere, and might not see any of the hot surface. This condition, limb darkening, would be characterized by temperature decreasing at the edges of the planet as it were approached. An instrument's capability or resolution much higher than that available from the Earth was required to resolve the limb brightening or limb darkening controversy. Mariner's radiometer would be able to provide something like 100 times better resolution than the Earth-based measurements. At 11:59 a.m. PST on December 14, 1962, Mariner's radiometers began to scan the planet Venus in a nodding motion at a rate of 0.1 degree per second, and reaching an angular sweep of nominally 120 degrees. The radiometers had been switched on 6.5 hours before the encounter with Venus, and they continued to operate for another hour afterward. The microwave radiometer looked at Venus at a wavelength of 13.5 millimeters and 19 millimeters. The 13.5 millimeter region was the location of a microwave water absorption band within the electromagnetic spectrum, but it was not anticipated that it would detect any water vapor on Venus. These measurements would allow determination of atmospheric radiation, averaging the hot temperatures near the surface, the warmer clouds at lower levels, and the lower temperatures found in the high atmosphere. If the atmosphere were a strong absorber of microwave energy at the 13.5 millimeters, only the temperature of the upper layers would be reported. Unaffected by water vapor, 19 millimeter radiations could be detected from deeper down into the cloud cover, perhaps from near or at the planet's surface. Large temperature differences between the 19 and 13.5 millimeter readings would indicate the relative amount of water vapor present in the atmosphere. The 19 millimeter radiations would also test the limb brightening theory. During its scanning operation, Mariner telemetered back to Earth about 18 digital data points, represented as voltage fluctuations in relation to time. The first scan was on the dark side, going up on the planet. The distance from the surface was 16,479 miles at mid-scan, and the brightness temperature was 369 degrees Fahrenheit. The second scan nearly paralleled the terminator, junction of light and dark sides, but crossed it going down. It was made from 14,957 miles at mid-scan and showed a temperature of 566 degrees Fahrenheit. The final scan, 13,776 miles at midpoint, showed 261 degrees Fahrenheit as it swept across the sunlit side of Venus in an upward direction. The brightness temperature recorded by Mariner's radiometer is not the true temperature of the surface. It is derived from the amount of light or radio energy reflected or emitted by an object. If the object is not a perfect light emitter, as most are not, then the light and radio energy will be some fraction of that returned from a 100% efficient body, and the object is really hotter than the brightness measurement shows. Thus, the brightness temperature is a minimum reading, and in this case was lower than the actual surface temperature. Mariner's microwave radiometer showed no significant difference between the light and dark sides of Venus, and, importantly, higher temperatures along the terminator or night and day line of the planet. These results would indicate no ionosphere supercharged with electrons, but a definite limb darkening effect, since the edges were cooler than the center of the planet. Therefore, considering the absorption characteristics of the atmosphere and the emissivity factor derived from the earlier JPL radar experiments, a fairly uniform 800 degrees Fahrenheit was estimated as a preliminary temperature figure for the entire surface. Venus is, indeed, a very hot planet. Cloud temperatures. The infrared readings. Mariner 2 took a close look at Venus's clouds with its infrared radiometer during its 35-minute encounter with the planet. This instrument was firmly attached to the microwave radiometer, so the two devices would scan the same areas of Venus at the same rate, and the data would be closely correlated. This arrangement was necessary to produce in effect a stereoscopic view of the planet from two different regions of the spectrum. Because astronomers have long conjectured about the irregular dark spots discernible on the surface of Venus's atmosphere, data to resolve these questions would be of great scientific interest. If the spots were indeed breaks in the clouds, they would stand out with much better definition in the infrared spectrum. If the radiation came from the cloud tops, there would be no breaks, and the temperatures at both frequencies measured by the infrared radiometer would follow essentially the same pattern. The Venusian atmosphere is transparent in the 8-micron region of the spectrum, except for clouds. In the 10-micron range, the lower atmosphere would be hidden by carbon dioxide. If cloud breaks existed, the 8-micron emissions would come from a much lower point, since the lower temperature is fairly transparent at this wavelength. If increasing temperatures were shown in this region, it might mean that some radiation was coming up from the surface. As a result of the Mariner 2 mission, scientists have hypothecated that the cold cloud cover could be about 15 miles thick, with the lower base beginning about 45 miles above the surface and the top occurring at 60 miles. In this case, the bottom of the cloud layer could be approximately 200 degrees Fahrenheit. At the top, the readings vary from about minus 30 degrees Fahrenheit in the center of the planet to temperatures of perhaps minus 60 degrees to minus 70 degrees Fahrenheit along the edges. This temperature gradient would verify the limb darkening effect seen by the microwave radiometer. At the center of Venus, the radiometer saw a thicker, brighter, hotter part of the cloud layer. At the limbs, it could not see so deeply, and the colder upper layers were visible. Furthermore, the temperatures along the cloud tops were approximately equally distributed, indicating that both 8 and 10 micron channels penetrated to the same depth, and that both were looking at thick, dense clouds quite opaque to infrared radiation. Both channels detected a curious feature along the lower portion of the terminator, or the center line between night and day sides of the planet. In that region, a spot was shown that was apparently about 20 degrees Fahrenheit colder than the rest of the cloud layer. Such an anomaly could result from higher or more opaque clouds, or from such an irregularity as a hidden surface feature. A mountain could force the clouds upward, thus cooling them further, but it would have to be extremely high. The data allow scientists to deduce that not enough carbon dioxide was present above the clouds for appreciable absorption of the 10-micron region. This effect would seem to indicate that the clouds are thick and that there is little radiation coming from the surface. And if present, water vapor content might be 1/1000th of that in Earth's atmosphere. Since the base cloud is apparently at very high temperature, neither carbon dioxide nor water is likely to be present in quantity. Rather, the base of the clouds must contain some component that will condense in small quantities and not be spectroscopically detected. As a result of the two radiometer experiments, the region below the clouds and the surface itself take on better definition. Certainly, heat trapping of infrared radiation, or a greenhouse effect, must be expected to support the 800-degree Fahrenheit surface temperature estimated from the microwave radiometer data. Thus, a considerable amount of energy-blanketing carbon dioxide must be present below the cloud base. It is thought that some of the near-infrared sunlight might filter through the clouds in small amounts, so that the sky would not be entirely black, at least to human eyes, on the sunlit side of Venus. There also may be some very small content of oxygen below the clouds, and perhaps considerable amounts of nitrogen. The atmospheric pressure on the surface might be very high, about 20 times the Earth's atmosphere, or more, equivalent to about 600 inches of mercury compared to our 30 inches. The surface, despite the high temperature, is not likely to be molten because of the roughness index seen in earlier radar experiments and other indicators. However, the possibility of small molten metal lakes cannot be totally ignored. The dense high-pressure atmosphere and the heat-capturing greenhouse effect could combine over long periods of time to carry the extremely high temperature around to the dark side of Venus, despite the slow rate of rotation and possibly accounting for the relatively uniform surface temperatures apparently found by Mariner 2. The radar profile. Measurements from Earth. In 1961, the Jet Propulsion Laboratory conducted a series of experiments from its Goldstone, California DSIF station, successfully bouncing radar signals off the planet Venus and receiving the return signal after it had travelled 70 million miles in 6.5 minutes. In order to complement the Mariner mission to Venus, the radar experiments were repeated from October to December 1962, during the Mariner mission, using improved equipment and refined techniques. As in 1961, the experiments were directed by W.K. Victor and R. Stevens. The 1961 experiments used two 85-foot antennas, one transmitting 13 kilowatts of power at 2,388 megacycles, the other receiving the return signal after the round trip to and from Venus. The most important result was the refinement of the astronomical unit, the mean distance from the Earth to the Sun, to a value of 92,956,200 miles, plus or minus 300 miles. Around 1910, the astronomical unit plotted by classical optical methods was uncertain to 250,000 miles. Before the introduction of radar astronomy techniques, such as those used at Goldstone, scientists believed that the astronomical unit was known to within 60,000 miles. But even this factor of uncertainty would be intolerable for planetary exploration. In radar astronomy, the transit time of a radio signal moving at the speed of light, 186,000 miles per second, is measured as it travels to a planet and back. In conjunction with the regular measurement techniques used by earlier investigators, this method permits a more precise calculation of the astronomical unit. Optical and radar measurements of the astronomical unit differ by 50,000 miles. Further refinement of both techniques should lessen the discrepancy between the two values. The 1961 tests also established that Venus rotates at a very slow rate, possibly keeping the same face towards the Sun at all times. The reflection coefficient of the planet was estimated at 12%, a bright value similar to that of the Earth and contrasted with the Moon's 2%. The average dielectric constant, conductivity factor of the surface, seemed to be close to that of sand or dust, and the surface was reported to be rough at a wavelength of 6 inches. The surface roughness was confirmed in 1962. Since it is known that a rough surface will scatter a signal, the radar tests were observed for such indications. Venus had a scattering effect on the radar waves, similar to the Moon's, probably establishing the roughness of the Venusian surface as more or less similar to the lunar terrain. Some of the most interesting work was done in reference to the rotation rate of Venus. A radar signal will spread in frequency on return from a target planet that is rotating and rough enough to reflect from a considerable area of its surface. The spread of 5 to 10 cycles per second noted on the Venus echo would suggest a very slow rotation rate, perhaps keeping the same face towards the Sun or possibly even in a retrograde direction opposite to the Earth's. In the Goldstone 1962 experiments, Venus was in effect divided into an observation zone, and the Doppler effect, or change in the return signal from these zones, was studied. The rate of rotation was derived from 3 months of sampling with this radar mapping technique. Also, the clear, sharp tone characteristics of the transmitted radar signal was altered on return from Venus into a fuzzy, indistinct sound. This effect seemed to confirm the slow retrograde rotation, as compared with the Earth, indicated by the radar mapping and frequency change method. In addition to these methods of deducing the slow rotation rate, 2 other phenomena seemed to verify it: a slowly fluctuating signal strength and the apparent progression of a bright radar spot across the center of Venus towards the outside edge. As a result, JPL scientists revised their 1961 estimate of an equal Venusian day and year consisting of 225 Earth days. The new value for Venus's rotation rate around its axis is 230 Earth days, plus or minus 40 to 50 days, and in a retrograde direction, opposite to synchronous or sun-facing, assuming that Venus rotates on an axis perpendicular to the plane of its orbit. Thus, on Venus, the Sun would appear to rise in the west and cross to the east about once each Venusian year. If the period were exactly 225 days retrograde, the stars would remain stationary in the sky, and Venus would always face a given star rather than the Sun. A space traveller, hovering several million miles directly above the Sun, would thus see Venus at almost stopped in its rotation, and possibly turning very slowly clockwise. All the other planets of our system, including the Earth, rotate counterclockwise, except Uranus, whose axis is almost parallel to the plane of its orbit, making it seem to roll around the Sun on its side. The rotation direction of distant Pluto is unknown. The Goldstone experiments also studied what is known as the Faraday rotation of the plane of polarization of a radio wave. The results indicated that the ionization and magnetic field around Venus are very low, and these data tend to confirm those gathered by Mariner's experiments close to the planet. The mass of Venus was another value that had never been precisely established. The mass of planetary bodies is determined by their gravitational effect on other bodies, such as satellites. Since Venus has no known natural satellite or moon, Mariner approaching closely enough to feel its gravity would provide the first opportunity for close measurement. The distortion caused by Venus on Mariner's trajectory as the spacecraft passed the planet enabled scientists to calculate the mass with an error probability of 0.015%. The value arrived at is 0.81485 of the mass of the Earth, which is known to be approximately 13.173 septillion pounds. Thus, the mass of Venus is approximately 10.729 septillion. In addition to these measurements, the extremely precise tracking system used on Mariner proved the feasibility of long-range tracking in space, particularly in radial velocity, which was measured to within 1/10 of an inch per second at a distance of about 54 million miles. As the mission progressed, the trajectory was corrected with respect to Venus to within 10 miles at encounter. An interesting result was the very precise location of the Goldstone and overseas tracking stations of the DSIF. Before Mariner 2, these locations were known to be within 100 yards. After all the data have been analysed, these locations will be redefined or relocated to within an error of only 20 yards. Mariner not only made the first successful journey to Venus, it also helped pinpoint spots in the Californian and Australian deserts and the South African veldt with an accuracy never before achieved.